Hello, very good morning to every one of you. So today we are going to begin with a brand new chapter. This is chapter 4, where in this chapter we are going to talk about periodic table and periodicity. Ready? Right. So without further ado, shall we begin? All right. So this is what we are going to learn throughout the chapters, where we are going to learn atomic and physical properties of the period 3 elements. We're also going to learn the reaction of the period 3 element with oxygen, and finally the acid-base properties of the oxides of the period 3 elements. Okay, so let's start off with the atomic and physical properties of the period 3 elements. Yeah. Okay, so before we go into the physical properties, let's have a little bit of the introductions to what is actually inorganic chemistry. Okay, so what is inorganic chemistry? Inorganic chemistry deals with the properties of all the elements inside the periodic tables. So it ranges from the highly reactive metals such as sodium to noble metals such as gold. The nonmetals include solid, liquid, and gases. So although this variety and diversity are features in many studies of inorganic chemistry, they are underlying a pattern and trends which enrich and enhance our understanding of the discipline. So these trends of the reactivity, structure, and properties of the elements and their compounds provide an insight into the landscape of the periodic tables and provide a foundations. So the periodic tables provide an organizing principles that coordinates about and rationalize the diverse physical and chemical properties of the elements inside the periodic tables. So what can we eventually tell or extract from the informations inside the periodic tables, right? Okay, so showing to you here is the modern periodic tables that we often see in any references of chemistry, where so going vertically across here is what we call as the period in here. Okay, so this is called as period. So therefore you shall have period 1, period 2, period 3, period 4, period 5, period 6, period 7. All right. Okay, and then going horizontally down to this one. Okay, so you have uh, for the first this one we have group 1, group 2, okay, group 13, 14, 15, 16, 17, and 18. So from group 1, 2, 13, 14, 15, 16, 17, 18 is what we call as a main group elements. Main group elements. Okay, and then we also have another set of the elements which lie somewhere in between here. Group 3, group 4, group 5, group 6, group 7, group 8, group 9, group 10, group 11, group 12. So all these group from group 3 until group 12 is what we call as D blocks elements, okay, and some of them are transitions elements, okay. And then we have a lanthanide series and actinide series, which we also known as these rare earth elements in here, okay. So as we learned during the when we learn about chapter 2, we call this group as the S blocks members, okay, where the valence electrons are remaining as. Okay, then we call all these blocks p blocks elements, okay, whereas this one we call it as a d block elements, and then finally we have so-called as the f blocks elements in here, okay. So each of these groups has a unique trends in their own way because they share the same valence electrons, which are classified accordingly based on their groups. Okay, so they will possess similar chemical properties and which going down to the groups changing with its reactivities going down to the group from there, right? Okay, so with that, that is for the introduction part of these periodic tables, right? Okay, so let's have a look at the content of our lesson today. So today we are going to learn about atomic and physical properties of the period 3 elements. So at the end of the lesson, you should be able to explain the trend of atomic radius, including the terms effective nuclear charge and shielding effect or screening effect. Explain the trends of melting point in terms of structure and bonding. Explain the electrical conductivities by applying the concept of the band theory. Difference conductor, semiconductor by using band gaps, explain the trend of the first ionization energy, and reduce the electronic configuration and the group of unknown elements based on the successive values of the ionization energy. Right. So let's have a look first at the introductions towards the physical properties. So showing to you in here is the period 3 physical properties. So who are the period 3 members? So our period 3 members include sodium with the formula Na, magnesium Mg, aluminium Al, silicon Si, phosphorus P, sulfur S, chlorine argon Cl, and argon Sar, with the increasing proton number from 11 until 18. Okay, so let's have a look at the trend of these physical properties generally, and then we are going to discuss one by one of their properties. Starting from the first one, atomic radius. As you can see from the values in here, you can generally conclude that when going across the period, atomic radius decrease. Okay, all right. As for the melting point, the trend goes by. The melting point increased from sodium to magnesium to aluminium, and then increased sharply to silicon, okay, and then decreased sharply to phosphorus, and then increased to sulfur, and then decreased to chlorine, and then argon has the lowest boiling point among all, melting point among all of them. Okay, so this is for the trend of the ionization melting point. As for ionization energy, generally across the period, ionization generally increase, though there are some anomalies in here. As you can see, the anomalies lies at between magnesium to aluminium, where magnesium is slightly higher than that of aluminium, and the other one is phosphorus and sulfur, where phosphorus is slightly higher than sulfur. So there is a reason behind this explanation, which we are going to explore together. And also electronegativity. So in terms of electronegativity increase going across period 3 in here. Okay. Okay, last but not least, as for the terms of conductivity of the elements, so sodium, magnesium, and aluminium are conductor. Okay, silicon is the semiconductor, and then the phosphorus are insulator. Okay. Okay, so how are they classified? They are classified based on their metallic properties, where sodium, magnesium, aluminium are metals, silicon is a metalloid, and then phosphorus, sulfur, chlorine, argons are non-metals, right? Okay, so with that, that is introductions to the physical properties of the period 3 elements here. So without further ado, let's have a look one by one at the physical properties of these period 3 elements, starting with atomic radius. So what is actually atomic radius, and what is actually atomic radius? So atomic radius is defined as the distance between the nuclei, half of the distance between the nuclei of the two closest identical atoms, or half of the closest internuclear distance. Okay, so in atomic radius, we can generally divide it into two types: covalent radius, which is possessed by most of the metalloid and non-metal, and then metallic radius for metals in here. Okay, so how do we measure in between the covalent radius and also atomic radius? So in covalent bond, okay, in the covalently bonded molecule, some of the molecules are polyatomic molecules, such as, for example, chlorine, fluorine, bromine, okay? And how is their atomic radius being measured? Now, don't forget, they are actually sharing the electrons in between the two atoms of the chlorine here. So their atomic radius is measured because some of the orbitals are overlapped, okay? So we have to measure based on the distance between two nuclei of the chlorine. Okay, so in this case, the distance between the two nuclei, which is also known as the bond length, is 198. So covalent radius take half of it. Okay, so take half of it, where this is it, and therefore it is 99 nanometers in here. So this is how we are going to measure the atomic radius for a covalently bonded compounds. Okay, whereas for the metals, okay, so in the metals, you have, because of the orderly arranged manner inside the metal atoms, Okay, so they have a proper distance in between two metals in here. So we first measure the distance between the two nuclei in here. When the distance between the two nuclei, let's say for aluminium, is 286 picometer. Okay, so uh, the metallic radius take half of it, which is 143 picometer. It's actually pico, not nanon, because they're supposedly to be very small in here. Sorry for the misinformation in here. Okay, they are supposed to be picometer. Okay, so this is how we are going to differentiate between a covalent radius and metallic radius, though it is not very important for you to distinguish between metallic radius and also covalent radius, because at the end of the day, we just want to compare the trends of this radius across the elements in the period tree in here. Okay. Okay, so what are the factors that affecting the atomic radius? So there are generally two factors that affects the atomic radius, and conclusively there is one which we summarize by the effective nuclear charge in here. Okay, so the two factors are nuclear charge and also screening effect. So let's have a look of what are nuclear charge and what are screening effect. Now, from the terms nuclear charge, so it is obviously nuclear or nucleus with charge. So in nucleus, we have two subparticles, which is proton and neutron. So which one has charge? It is proton. So when we say nuclear charge, it is referring to the number of protons inside the atoms. Okay. So technically, we say that when you have a higher greater the number of proton, higher the nuclear charge in here. Okay. Okay, so this is for nuclear charge. And then for screening effect, so screening effect, or sometimes also known as the shielding effect, is the shield formed as a result of the repulsion by the electrons either within the shell or between the shell. Okay, so for early period, which is for example first shell to second shell to third shell, the repulsion between the shells are more significant. Okay, so when you have the repulsion between the shell, it reduces the attraction between the nucleus and the outermost electrons in here. So in general, we say that greater the number of shell, greater the screening effects in here. Okay. So from here you can see what is the difference about nuclear charge, and in here this is the screening effects in here. Okay. Okay, so now you have already know the two factors that influence the atomic radius. It is then concluded by effective nuclear charge, okay, which is also known as Z effective. It is the nuclear charge felt by an electron when both the actual nuclear charge and screening effect of the other electrons are taken into account. So in general, we say that nuclear charge, effective nuclear charge is equals to nuclear charge minus the screening constant. Of course, this is just a qualitative description to describe how strong it is the attraction between the nucleus to the outermost electron. So therefore, generally, we are going to say that greater the effective nuclear charge, stronger the attraction forces between the outermost electron to the nucleus of an atom here. Okay, so I shorten it. So in short, it says that atomic radius is affected by nuclear charge and screening effect. By nuclear charge is referring to the number of proton, screening effect is referring to the number of shells in here, and then concluded by effective nuclear charge. Okay. Okay, so what is the trend of the atomic radius when going across period and when going down to the group, and how are we going to describe them? So let's start off first from the trend of the atomic radius going across period 3. So generally, as you can see in here, atomic radius decrease when going down to the group in here. Okay, so how are you going to describe this? So as proton number increase, the nuclear charge increase. However, as electrons are filling in the same shell, so screening effect we say here remain almost constant. Okay, because the repulsions between the electrons are not that significant in the same shell. Okay, as a result, effective nuclear charge increase. Therefore, the attraction between the nucleus and the outermost electron becomes stronger, and that is why the electrons are pulled closer towards them. Okay, so this is a trend of atomic radius when going across period 3. So what about the trend of the atomic radius when going down to a group? Okay, so no matter what groups that we are talking about, so when going down to any group, atomic radius increase. So this is exemplified by, I think this is a group 1, okay? Why? So as the proton number increase, the nuclear charge increase. However, as more electrons are filled in the shells, screening effect also increase because you require more shells to filling in more electrons as going down to the group. As a result, effective nuclear charge is increased slightly due to the massive number of the protons, but yet because of number of shells is more significant, atomic radius increase. So this is how we are going to describe the trend of the atomic radius when going down to the groups in here. Okay. Okay, so with that, that is a trend of the atomic radius going across period and going down to the groups. Finishing the atomic radius, we are going to talk about ionic radius. But before we going down talk about ionic radius, let's understand on how ion is formed. So an ion is formed when atoms donate or receive electrons. Okay? So when an atoms donate electrons, what will happen? When an atoms donate electron, it become a positively charged ions. Generally, from the equation, A give A plus plus E minus. Whereas a negatively charged ions is caused by receiving electron, okay, where in here you have the half equation, x plus E minus give x minus in here, okay. So from in terms of the size of the ions, right, for the atomic radius, for the cation, okay, so you can see that the atomic radius is larger than that of the cationic radius. I repeat, atomic radius is larger than that of the cationic radius in here. So why is it happening? Let's use magnesium as the example. So magnesium has the electronic configuration of 1s2, 2s2, 2p6, 3s2. So in other words, magnesium uses three shells. When two electrons were donated from the 3s orbitals, so it formed magnesium 2 plus, which has 1s2, 2s2, 2p6. So obviously, the number of the shell has decreased while the nuclear charge still remain the same. So the effective nuclear charge increase and therefore decrease the distance between the nucleus and the outermost electrons in here. So this is for cation. Now, as for anion, okay, so the atomic radius is smaller than that of the anionic radius. Okay, so let's use phosphorus as examples, where phosphorus has the electronic configurations of 1s2, 2s2, 2p6, 3s2, 3p3. As phosphorus accepts 3 electrons to form p3 minus, where you have 1s2, 2s2, 2p6, 3s2, 3p6, the effective nuclear charge decreases as the shell is complete filled, where you have octet configuration. So when there is an increase in number of the electrons, the screening effect is increasing more significant. So that is why the effective nuclear charge decrease. Okay, so here are the trends of the atomic and ionic radius from different groups here. Okay, so highlighted in the green color is for non-metals, and highlighted in the purple color is for the metals in here. Okay, so we are I purposely select some of the successive proton number for phosphorus, sulfur, chlorine to sodium and potassium and also calcium. Okay. So in terms of the ionic radius, okay. So let's focus first on the anionic radius first, shall we? Okay. So in anionic radius here, okay. You see, from phosphorus, phosphide ion, sulfide ion to chloride ion, as you can see from these values in here, is that the value decreasing. Okay. So why is it that the value is decreasing? So if you look carefully inside here, okay, sulfur has the valence electron of 3s2, 3p4. Chlorine has the valence electron of 3s2, 3p5. Okay, so after accepting two electrons for the sulfur to become sulfur ion, we have 3s2 3p6. As the chlorine, you accepted one electron to form chloride ion with the valence electron 3s2 3p6. Okay, so phosphide, as we also mentioned just now, 3s2 3p6. So they have the same number of electrons. Okay, so for same number of electrons in here, we have a special term for it. We call it as isoelectronic. Okay, so when you have the same number of electrons, we say that the screening effect are the same or remain constant. So can okay. So as you can see, as the proton number increase, the nuclear charge increase, while the screening effect remain almost constant. Therefore, the effective nuclear charge will also increase, isn't it? Okay. So therefore, the ions become smaller. So from the T3 minus to S2 minus to Cl minus. Okay, so this is from the perspective of a negatively charged ions. Okay, as from the perspective of a positively charged ion, so we shall have a look at the potassium and also calcium in here. So potassium has the valence electron of the 4s1, while calcium has the valence electron of 4s2. After donating one electron, you form 3s2 3p6. Calcium also form 3s2 3p6. Okay, so they are also isoelectronic, therefore screening effect remain almost constant. Okay, so as the nuclear charge increase while screening effect remain constant, effective nuclear charge increase. So that is why the ionic radius of the potassium is much larger compared to the ionic radius of the calcium in here. Okay. All right. So now we have separately see the effects of the uh, ions from different groups. So when we compare overallly from phosphorus to sulfur to chlorine to argon, and as we already witnessed just now, all of them has the same valence electron, which is 3s2 3p6 for all these ions in here. Okay, so all this has same number of electrons. Therefore, we are calling them as isoelectronic in here. Okay. So when going across from phosphorus to sulfur to chloride, sorry, phosphide ion to sulfide ion to chloride ion to potassium to calcium ion, ionic radius decrease. Okay, so how are you going to describe them? When going across this ion, nuclear charge increase as the number of proton increase. However, all these ions are isoelectronic. That means they have the same number of electrons. Hence, the screening effect of these ions remain constant. So this will cause the effective nuclear charge to increase, which results the attraction forces between the nucleus and the outermost electron to become stronger, therefore decrease the ionic radius. Okay. All right, with that, that is all for the first part of our video for chapter 4 today. And I'll see you in our next part of the video. All right, have a great day.